Hello and welcome to this tutorial video on vector algebra. In this lesson 3, we will be exploring the concepts of vector equation of lines. In our previous lessons, we covered the basics of vectors, including vector addition, scalar multiplication, and the dot product. Now we are going to take it a step further and learn how to represent lines in a vector form. This is a crucial concept in mathematics and in physics, as it allows us to describe the position and direction of lines in a more elegant and an efficient way. In this lesson, we will be covering the following topics: the concept of a line in vector form, the equation of a line or vector equation of a line, the direction vector and position vector of a line, the parametric form of a line equation, and how to write a vector equation. By the end of this video, you have a solid understanding of the vector equation of lines and be able to apply it to solve problems. Now let's get started. We are seeing that a straight line is uniquely determined in space if there is a point on it and its directions are given, or 2 points on it are given. What are we trying to mean here? We want to emphasize that a straight line in space can be either be known by a point on it, or either by knowing a point it passes through and the direction it is heading, or by knowing two distinct points that the line is passing through. And so for that matter, equation of a line passing through a given point and parallel to a given vector. So in vector form, in this figure here, we are saying that if there is a line which is given as A, or there is a line passing through point A, and this point is vector with respect to the origin as indicated here, and this same vector, this line is also parallel to a vector in space which is V. So there is a line which is passing through A, and this particular A is having a position vector with respect to the origin, and this line that is passing through A is also parallel to a given vector in space which is V. Now we are also saying that if there is any point on the line and it's also parallel to the vector V, then that point too also is having a vector with respect to the origin. And so let's assume that the vector is R. Then we have that our vector OA is equal to the small letter A, and our OP is equal to our vector R as indicated here. So since OA and V are parallel, so since this one is also parallel to this, then we can say that the line AP or the vector AP is equal to a certain number times the vector V. So this line that we see here, we are saying that this is equal to a certain number times the vector. Of course, we are talking about a form of a certain number or a scalar that multiplies the vector to give us this. And so if OA and V are parallel, then AP is equal to a certain scalar times the vector. But we know that AP is also equal to OP minus OA. And so OP from the diagram here is vector R, and then our OA is vector A. And then we have expressed OAP in this form. So in place of OP, AP here, we can put this one over here. So we will have R minus A equals a certain scalar times the vector V. So we will have R minus A equals to CV. Now, let's make R the subject here. Now, if we make R the subject, then it means we are going to have R equals to A plus a certain scalar times V, and that is what we have. So this equation that we have here is called the vector equation of the given straight line. So this is the vector equation of the given straight line. Okay, T is a variable scalar or it's just a parameter, and so is the parametric vector equation of the line. Corollary: if the straight line is given to be passing through the origin, then the vector equation becomes R equals to T V. Okay, now let's check something. Cartesian form of vector equation. Now let the coordinates of the fixed point A be x1, y1, and z1 in a 3D coordinate system, and the direction ratios of the parallel vector be A, B, C. Then we are saying that A is equal to x1 ij y1 j plus z1 k, and the vector V is having this as its component. Then we have our R2 as xi plus yj plus zk. Since we are saying that the vector equation R is equal to A plus TV, when we make the substitution, we have our R to be here. So we have our R, we have our R to be here. So when we substitute, we are going to have xi plus yj plus zk, and it is equal to A. Our A is x1i y1j plus z1k, and that is what you have, plus a certain scalar times A and a certain scalar times V, and our V is x AI plus BJ plus CK. Alright, so when we equate the coefficients of I, J, and K, so let's equate the coefficients of I, J, and K. We have xi equals x1i plus, so a corresponding xi component. So we have this one, we also have this one here, and then we have this. So plus T A I. Now let's try to remove all the i's. Then it means we are going to have x is equal to x1, sorry, this one is 1 plus C A. We are removing all the i's. So we have x is equal to x1 plus TA, and that is what we have here. Now let's talk about the next one, which is J. So equating corresponding J components, we have yj equals y1j plus tbj. So let's remove all the j's. You have our y to be equal to y1 plus tb. And so as well as for the last one, we are going to have z to be equal to z1 plus ctc. Okay, now let's equate all the x, or yes, so let's equate all our t's. So in this particular equation, x equals x1, x equals x1 plus ta. If we have to make a rearrangement, we are going to have x minus x1 equals to ta. So we divide here by a, we divide here 2 by a. Therefore, we're going to have t is equal to x minus x1 all on a. So this is for the first one. So the second one as well, we are going to have t is equal to y minus y1 on b. And the last one is going to be t equals to z minus z1 on c. So if we, these are all in terms of t's. So therefore, we can say that t is equal to the whole of this equals to this equal to that. So this is the solution that we have for this one. So if you eliminate all the t's, then it means that x minus x1 on a equals y minus y1 on b equals z minus z1 on c. So this is the Cartesian or the symmetric equation of the line passing through a point x1, y1, z1 and parallel to a vector whose directions are a, b, c. Non-parametric vector equation. The non-parametric vector equation is given as AP times V equals 0. So vector AP times V equals 0. And we know that AP is equal to OP minus OA. But OP is R and OA is A times V, which is this, is equal to 0. So when we multiply through by V, we are going to have R times V minus A times V, and this is equal to 0. So if we bring this one here, we are going to have R times V is equal to A times V. This is the non-parametric vector equation of the line. Now let's take an example. Find the vector in the Cartesian equations of the straight line passing through the points 5, 1, 3 and parallel to the vector I plus 4j minus 2k. Okay, so we know that the vector equation of the line through the point with position vector A and parallel to the vector V is given by R, where t is a scalar. So the vector equation which we have as A plus CV. Now let's make the substitution. We are saying that the position vector is A, and for that matter, our position vector is this, which is 5i plus j plus 3k. So if we make the substitution, we are going to have 5i plus j plus 3k, then plus a certain scalar which is t times the v which is I plus 4j minus 2k. Okay. Or in other words, if we are to equate the corresponding I components, we are going to have 5 plus ti. Yet so we have 5 plus t or I. So this one 5i, this one to t times I. So we are going to have ti for this. So this is all about I. And then the next one is, this is 1. So we are going to have 1 plus 4t in j. And then the last one is 3 plus negative 2t. So 3 negative 2t or minus 2t, or in terms of k. So the Cartesian equation of the line passing through x1, y1 and parallel to the given vector is also given as x minus x1, y minus y1, x minus x1 on A equals y minus y1 on B equals z minus z1 on C. And we know that our x1, y1 z1 is equal to 5, 1, 3, and our ABC is also giving us 1, 4, -2 from the question. So the 5, 1, 3 becomes the vector equation, the R, which is this that was given to us in the question. And then our ABC equals to this. So we have A to be 1, B is equal to 4, and C is equal to -2. And then our X1 is this, our Y1 is this, and then our Z1 is this. Okay, so by substitution, we are going to have x minus x minus x1 on A. So x1 is 5. So here our x1 is 5 on A, and then here our A is 1. So on 1 is equal to our y12 is 1 on our B, which is 4. So 4 is equal to our Z12 is 3, and then our C is -2. So we are going to have it this way. So x minus 5 on 1 is the same as x minus 5. So we are going to have x minus 5 equals y minus 1 on 4 equals -z minus 3 on 2. Equation of a straight line passing through two given points. So let's say, as we saw in our introduction, we said a straight line could pass through these two distinct points. So we are going to find an equation where the straight line passes through a given point in a vector equation form. So we are saying that let a line pass through two given points, say A and B, whose position vectors are this and that. Okay, right. So if we have a straight line whose position vector passes through a given point, let's say A and B, then if we let any P be any point on the line and its position vector be R, then OA is equal to this, OB equals to that, and OP equals to R. Since we have two given points, we have AP and AB being parallel vectors. For that matter, we can say that our AP is equal to now CAB for some scalar t. Also, OB, AB is equal to OB minus OA. And AP is also equal to OP minus OA, which is equal to this. Now we know that our OP, our OA is also R minus A respectively. It's equal to, and then our OP is B, and then our OA is A. So when we make rearrangements, we are going to have R is equal to A plus T on T times A minus T times B minus A. That is great. Or in other words, we can also say that this is also equal to 1 minus T times A plus CB. Of course, when you expand this, you get back to the first one over. So this represents the vector equation of a line passing through two given points. And then the Cartesian coordinates or the Cartesian form of that equation is also given as this. Since we have 2 points, then it means we are going to have our first coordinate for the first point to be x1, y1, and z1. And then for the second point, we are going to have the coordinate to be x2, y2, z2. So if A is equal to this, and then B is equal to that, and R is equal to this, Then when you substitute these values into the equation, then you are going to have this times a certain number, which is t of a minus this one too. So when we expand, then it means we are going to have our x to be equal to x1 plus t times x2 minus x1. Then our y2 will be equal to y1 minus t into bracket y2 minus y1. And then our z is equal to z1 plus t into bracket z2 minus z1. These are the parametric equations of the line. So when we see the subjects, of course, if we send this one here, for example, the z, let's take the last one and check it out. So if you have z equals z1 plus t into bracket z2 minus z1, then if you bring this one here, you're going to have z minus z1 equals t times z2 minus z1. So dividing here, you have z2 minus z1. So the whole of this is z2 minus z1. This one cancels, and t will be equal to z minus z1, z2, all on z2 minus z1. So for the other ones to follow the same approach. Okay, now let's take a question. And the non-parametric vector equation is also giving us this. Now find the vector and the Cartesian equations of the straight line passing through the points. We know that our vector equation of line passing through given points with their position vectors are a and vectors as a and b is given by this. So our a is equal to 2i plus 4j minus 3k, and then our b is equal to 3i minus j plus k. Okay, but b minus a is equal to our b is 3i minus j plus k minus our a is 2i plus 4j minus 3k. So subtracting corresponding components, we are going to have I minus, so this one is negative 1, this one is negative 4, so you are going to have 5j, this one is also 1 minus 3, which is negative times negative give us positive 3 here, so we are going to have 4k. So when we substitute that one here, we are going to substitute that one to here, and then our a is already giving us this. So when we make the substitution, then our vector equation is going to be our r, sorry, our vector equation is going to be 2i plus 4j minus 3k plus c into brackets. Our b is I minus 5j plus 4k minus our a. So we've already found that one too. So there's no need to rewrite this one. And we had our b minus a here to be I minus 5j plus 4k. Okay, alright. So the Cartesian vector equation, the Cartesian vector form of the equation is also giving us this. Our x minus x1 on x2 minus x1, as well as y minus y1 on y2 minus y1, and then z minus z1, then z2 minus z1. So we know that our x1 y1 is equal to this, and then x2 y2 is equal to the second coordinates of p. So when we make the substitution, then our x1 is x minus x1. So x1 is 2. So here is supposed to be 2. Our y1 is so x2 minus x1. So our x2 is 3 minus 2. So that gives us 1. And then our y1 is 4. So I'm going to have 4. And then y2 minus y1 is negative 1 minus 4. And that gives us negative 5. So we are going to have negative y minus 4 on 5. So there is a mistake here. And then our z is also z minus z1. And our z1 is negative 3. So it will be positive. On z2 is 1. Z1 is negative 3. So 1 minus negative 3. And that gives us 4. So we are going to have 4. So this is the Cartesian equation of the straight of the line passing through two given points. Now, in this part of the lesson 3, which is angle between two vectors, we are saying that let R be equal to, let a vector equation of this vector R equal to A1 plus TU, and then another vector 2 here, be any two lines in space, so which is also A2 plus SV. These are the vector equations of the lines. Okay, now these two lines are in the directions of the vector U and V. They are vector equations, of course, or vector equation of lines. But these vector equations that we see over here, these two are in the direction of the vector U and vector V. Now we are going to find the angle between two lines. So the angle between the two lines is defined as the angle between the two directions. So angle between these two lines is the same as the angle between two directions, and the directions are in U and V. So this is where we are going to find the angle. So if theta is the angle between the given lines, then our angle is given by the formula cos inverse U dot V on magnitude of U times magnitude of V. So this is the angle, the formula for finding the angle between two given lines. Now, if the equations of the lines are in Cartesian form, as we saw in our earlier discussions, then our x minus x1 on A1, y minus y1 on B1, z minus z1 on C1, and x minus x2 on A2, y minus y2 on B2, z minus z2 on C2. So where A1, B1, and A2, B2 are the direction ratios of the two lines, then if you are to find the angle between these two lines, then the formula is theta equals cos inverse of A1 times A2 plus B1 times B2 plus C1 times C2, all on root of x1 squared plus B1 squared plus C1 squared times root of A2 squared plus B2 squared plus C2 squared. When the two lines are perpendicular, so it means that if the two lines are perpendicular to each other, then A1 times A2, or the dot product between the two, is 0, as we saw in our lecture, our lesson 2. If the two lines are perpendicular, then the dot product between the two is 0. Now let's take a question. Find the angle between the plane x plus y plus z equals 1 and x minus 2y plus 3z equals 1. So the normal vectors of these planes are n1. So we have 1, 1, 1. So 1, 1, 1. And then our n2 is 1, negative 2, 3. Okay. Now, if theta is the angle between these two given planes, then we are saying that our cos inverse or cos theta is equal to n1 dot n2 over the magnitude of n1 times n2. So now let's find the dot product. So 1, 1, 1 dots, 1 negative 2, 3. So we are going to have 1 times, so 1 times 1 times this, plus 1 times negative 2, plus 1 times 3. So 1 times 1 is 1, 1 times negative 2 is negative 2, 1 times 3 is 3. So we have 4 minus 2, and that gives us 2. That's why we have it here. Okay, now we find the magnitude of n1. So the magnitude of n1 is equal to 1 squared plus 1 squared plus 1 squared. So and that gives us root 3. So for the first one over here. And for the second one, our magnitude of n2 gives us root of 1 squared plus negative 2 squared plus 3 squared. And that gives us root 14. Okay, so we have it over here. And so our cos theta equals the n1 dot n2 is 2 over root 3 times root 14. And that will give us 2 on root 42. So finding the cos inverse of 2 on root 42 gives us 25.21 degrees. So that's the angle between these two planes. Thank you, and don't forget to subscribe to our channel.